In this video, we are going over the concepts for the subject of biochemistry. Let's first establish that biochemistry is the branch of science that is concerned with the chemical processes and substances that occur within living organisms. Because of this, we understand that there are four major biomolecules that we must discuss that include carbohydrates, lipids, proteins, and lastly, nucleic acids. In that order, you're going to be watching videos discussing each of them. Let's get started with carbohydrates. When it comes to carbohydrates, they are a major source of energy in our diet. The chemical formulas for carbohydrates have the general formula of CnH2O(N), which means that these biomolecules contain carbon, hydrogen, and oxygen. Carbohydrates are also called saccharides, which means sugars. There are certain organisms and even plants that can synthesize these biomolecules by combining CO2, water, and in this case, energy from the sun. The process of photosynthesis is what allows this to happen, and carbohydrates like glucose can be made. The human body can synthesize them, but not by this process. What we can do really well is actually derive energy from these sources. So for example, when we have a glucose molecule react with O2 via the process of respiration, the human body can convert that glucose molecule to CO2, water, and energy. The energy molecules that we have in the body are called ATP, and we're going to learn about them when we talk about nucleic acids. But in general, when we actually explore in detail and look closely at the reaction of respiration, one thing that we can notice is that these carbohydrates, like glucose, when they're exposed to O2 and make these products, essentially what we're doing every time is a combustion reaction. There are different types of carbohydrates. Carbohydrates can come as one unit, which are known as monosaccharides. If your carbohydrate consists of two singular units of carbohydrate, they are known as disaccharides. And if your carbohydrate has many units of a monosaccharide, they're known as polysaccharides because they form a polymer. Monosaccharides particularly can be classified based on their carbonyl functionality and the number of carbons that are present in the monosaccharide. If a particular monosaccharide has an aldehyde functional group, then that monosaccharide is known as an aldose. If your monosaccharide has a ketone group, then that is known as a ketose. We can observe in the bottom examples of aldoses and ketoses, and we can even observe the functional groups that they have. In the case of the aldose, we see the aldehyde. In the case of the ketose, we have the ketone. Moreover, when we are trying to classify these monosaccharides, we can do it based on the number of carbons. And you can observe that specifically for monosaccharides, they have from 3 to 8 carbon atoms. So a monosaccharide that has 3 carbons is known as a triose. 4 carbons is known as a tetrose. 5 carbons is known as a pentose. 6 carbons is known as a hexose. A heptose has 7 carbon atoms, and octose has 8 carbon atoms. It is important to note that when you're trying to include both of these classifications in a single word, as you can see in the bottom of the slide, what we do is that for the aldose sugars, we only do ALDO followed by the classification of the carbon atoms. Next, if your monosaccharide has a ketone, then you put KETO followed by the number of carbons in order to classify it. So in the case of glucose, we can see that it's an aldohexose. And in the case of fructose, we can see that it is a ketohexose. One of the most common illustrations for open form of monosaccharides are Fisher projections. And specifically, what I would like to illustrate is the Fisher projection for glucose, galactose, and fructose, which are common monosaccharides. What this is illustrating is just the aldehyde functionalities, and at each intercept, there is a carbon atom that is holding on either side a hydroxyl group and a hydrogen. That's why carbohydrates are known as polyhydroxy aldehydes or ketones. One of the important features that can be observed in the structure of carbohydrates is that they are known as chiral molecules. Chiral specifically refers to anything that cannot be superimposed on its own mirror image. But at the basic definition of what makes a molecule chiral is the idea that a carbon atom is bonded to 4 different groups. So this means that the carbon atoms that are considered chiral must be tetrahedral, okay? So here we have the example of 2 different molecules, glyceraldehyde in the L form and glyceraldehyde in the D form. And you may be wondering, what is D or L? D or L is actually a configuration that can be given to particularly carbohydrates or even amino acids, depending on the groups that are in the molecule. So what establishes if a molecule is D or L? If we look closely at the example that we have here for erythrose, by definition, what happens is we determine the D and L notation for a monosaccharide by detecting the chiral carbon that is the farthest away from the carbonyl. In erythrose, so since the aldehyde is here, the chiral carbon is this one, okay? Why is that carbon chiral? Because essentially, I'm going to write in the carbon atom, it is connected to a hydrogen, a hydroxy group, this bottom part of the molecule, and the rest of the molecule on top. So that carbon is chiral. And since is the one that is the farthest away from the carbonyl, then we proceed to look at what is the position of the OH. Since in this molecule, the OH is to the left, that is the L version of the carbohydrate. If the OH is on the right side of the carbon within the monosaccharide, that is the D isomer. Now, let's note that that is not the only chiral center in the molecule. When we look at this carbon atom is also chiral. It's just that for defining D and L, only the one that I just put the asterisk is the one that determines D or L. Whenever these molecules have a relationship in terms of chirality, there are different definitions that can actually encompass what does this mean and the categories that are defined. D and L carbohydrates are specifically known as enantiomers. But let's go back into understanding why is it that they are known as enantiomers. Earlier in the semester, we learned about isomers. And isomers specifically are defined as two molecules that have the same chemical formula, but the attachment or the arrangement of atoms could be different, which results in different properties. Taking this into consideration, let's understand that we observed before constitutional isomers, because constitutional isomers are going to have same chemical formula, but the attachment of the atoms is different. Now, we also have additionally stereoisomers. And when it comes to stereoisomers, which are known as spatial isomers, there's two variations of them. First, we have diastereomers. And diastereomers, for the purpose of this class, is going to be two molecules that have the same name, but one is cis and the other one is trans. In the case of enantiomers is going to be two molecules that are chiral, but they are mirror images of each other and they cannot completely overlay. So by definition, when we have this D and L notation for carbohydrates, they are known as enantiomers. Enantiomers are very important in nature because enantiomers can trigger differently physiological responses. To give you an example, here we have the two enantiomers for the molecule naproxen. We can observe that if you have naproxen at home, which is commercially known as Aleve, the bottle will specifically have the anti-inflammatory agent that comes from the enantiomer that is labeled S. S and R, which is what you observe here, it is something that you will not be tested on. It just happens to be another way we can categorize enantiomers. Nevertheless, the R enantiomer, which you can see it here, is not present in the medicine because it actually triggers toxicity in the liver. So understand that many medicines have a particular enantiomer that it is present in the product because it's the one that is going to show physiological response. Now we are going to move on to talk about particularly monosaccharides, some of their chemical properties, and then we will proceed to talk about disaccharides and polysaccharides. When we talk about monosaccharides, three of the common monosaccharides are glucose, galactose, and fructose. Glucose, it is found in fruits, in corn syrup, and in honey. As you can observe, is an aldohexose because it has an aldehyde and it has 1, 2, 3, 4, 5, 6 carbon atoms. Glucose is also known as dextrose, and it is the sugar that we have in our body. Glucose is very important because it's the building block of many other disaccharides and polysaccharides. As you can see, sucrose, lactose, maltose are all disaccharides that come from glucose. And lastly, cellulose and glycogen are polysaccharides that are made from glucose. Galactose is actually an aldohexose, just similar to glucose. It is not found free in nature, but it can be obtained from the disaccharide lactose. The difference between glucose and galactose is that specifically at carbon number 4, the OH in galactose is pointing to the left instead of the right. That particular difference makes this molecule be a completely new substance. The relationship between these two molecules It is known as epimer, which is a new kind of isomer. So we know that galactose is an epimer of glucose. Lastly, we have fructose. Fructose can be obtained from sucrose, which is table sugar. It is a ketohexose. And we can observe that there is the ketone here, hexose, because we have 1, 2, 3, 4, 5, 6 carbon atoms. And out of the monosaccharides, it is actually sweeter than table sugar. Let's now have a brief discussion about the chemical properties of monosaccharides, starting with what the food industry has created in order to create calorie-free substances. One of the things that can be done with monosaccharides, even disaccharides, is that they can be reduced to make the molecules that are known as sugar alcohols. And a sugar alcohol is simply, if you have a monosaccharide, and here we have the example of xylose, the aldehyde that is in the molecule, upon exposure to hydrogenation conditions, is going to be changed into the primary alcohol. So we can observe how the molecule xylose can be changed into the sugar alcohol, xylitol. The name of sugar alcohols come from the fact that you are going to replace the ending OSE in your monosaccharide or carbohydrate, and then you're going to replace it with ITOL. So for example, if I have the monosaccharides glucose and I reduce it by hydrogenation, the alcohol that results is called glucitol, or in other words, sorbitol. The reason why I bring up xylitol is because for those students that are going into dental hygiene, it is known that xylitol, it is an important sugar alcohol that has been scientifically shown that it actually prevents cavities because the bacteria that form the cavities cannot use it. So actually eating candy from xylitol or made from xylitol can actually help you have just better oral health. So it's also been understood that this type of candies are suitable for diabetics, okay? The use of it was approved by the FDA, and it is actually sweet as sugar. So there is a company that has been developed by this young lady that you see in the picture that is called Solly Pops, and she made a chemical company creating candies using xylitol. Other than creating sugar alcohols, hydrolysis is another thing that can happen to carbohydrates. Specifically, hydrolysis only occurs with disaccharides and polysaccharides. Hydrolysis cannot happen with monosaccharides. It can be done under acidic conditions, or you can use biomolecules like enzymes in order to produce them. And as you can observe, the disaccharide upon hydrolysis is going to make the 2 monosaccharides that it contains in its structure. And when it comes to polysaccharides, then it's going to have many, many, many units of the monosaccharide that is made out of. Other type of reactions that can happen with monosaccharides include oxidation. And in the case of oxidation, this specifically can be utilized to detect glucose in particular solutions. The Benedict's reaction is a good example of this. In the Benedict's reaction, what happens is that the sugar, because adjacent to the carbonyl has a carbon with a hydroxyl group, can oxidize, and in turn, it can reduce copper 2 to copper 1, because this particular monosaccharide, glucose, can get oxidized and in turn reduce copper 2 to copper 1. That's why glucose is known as a reducing sugar. While the color of the Benedict's solution is blue, any change in color, changing to green, changing to yellow, changing to red, represents that the oxidation of the sugar has happened. In other words, the copper 2 reagent has been reduced. Another type of reaction that occurs in monosaccharides specifically is going to be the cyclization of a monosaccharide. In the cyclization of a monosaccharide, let's understand that the groups that are involved are going to be the OH that determines DNL versus the carbon in the carbonyl that we have in the molecule. Okay, so those are the two groups that react. In these type of structures, upon cyclization, and you can see the different structures right here, what happens is that we have an intramolecular reaction. And in this intramolecular reaction, the OH connects to the carbon in the carbonyl. And overall, let me zoom in so we can see it closely. The oxygen connects to the carbon. This oxygen becomes an OH because this hydrogen atom can then give the proton at this position. So we see overall that if I use my highlighter tool of how is it that this intramolecular reaction within the molecule happens, this oxygen atom is this oxygen. This carbon atom is this carbon. This oxygen atom is this oxygen. And even though people may suggest, where does the hydrogen come from for the purposes of this class, let's just have the assumption that this hydrogen is actually going to move here. That creates what is known as the anomeric carbon, but it is important to define that when this reaction happens, this is the formation of a hemiacetal functional group. This is not an ether. Lastly, to finish up the carbohydrates, let's talk about polysaccharides. When it comes to polysaccharides, let's understand that the ones that we have here are all built from glucose. Here we have 3 examples of polysaccharides. They include starch, which it can be found in nature. And starch is a polysaccharide that has many glucose molecules that are linked to one another in an alpha 1,4 linkage between the glucose molecules and an alpha 1,6 linkage. Okay. The alpha 1,4 and alpha 1,6 just defines the connectivity of the glucose molecules. Glycogen, which is how we store sugar in our body, also has alpha 1,4 and alpha 1,6. The difference between starch and glycogen is just that in our body, our glycogen molecule, which is also known as animal starch, it is more branched, meaning that these areas of the molecule where the glucose molecules extend from the original thread of glucose molecules. So think about it like a substituent. It's just really, really long in the molecule of glycogen. Lastly, we have cellulose. Cellulose, which is particularly found in plant cell wall, it is also a type of polysaccharide made out of glucose. But instead of having alpha-1,4 and alpha-1,6 linkages, it has beta-1,4 linkages between the glucose molecules. Now, when it comes to this, understand that one of the important things that happens when it comes to cellulose is that cellulose, we don't have the biomolecules to actually cleave this linkage. So that's why cellulose we cannot utilize as a source of energy.